Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the most extraordinary fates a star can meet, the moment it dies and what is quietly born in its place. We'll follow the story of the Neutron star, a city-sized remnant of a once mighty sun, dense enough to crush mountains into a teaspoon and calm enough to teach us how the universe reshapes itself after catastrophe. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these slow explorations enjoyable, and when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see how far this small constellation of sleepy minds reaches, from warm living rooms to quiet balconies under starlight. Now, take a deep breath. Maybe dim the lights, or let the room stay just dark enough that you can sense the hum of the night around you. If you have a cup of tea nearby, let it cool a little. We're not in a hurry here. As you listen, imagine yourself drifting among the stars, not racing past them, but floating slowly through the stillness between suns. Some of these stars are young and blazing, others are growing tired, their light softening as their fuel begins to fade, and somewhere out there, a few are approaching the end of their long story, preparing for a transformation so complete that even time itself will seem to pause. When you're ready, let's begin that story together. A star, for most of its life, is a balancing act written in light. Deep inside its heart, atoms are pressed so tightly together that they merge, hydrogen fusing into helium, helium into heavier elements, and with every fusion comes a little burst of energy. That energy pushes outward, countering the relentless inward pull of gravity. For billions of years, this perfect equilibrium continues, a quiet conversation between fire and weight. If you could listen closely to a star in its prime, it would sound like a steady breath. The warmth you feel on your skin from the sun each morning is part of that same breath, the gentle pressure that keeps it from collapsing under its own mass. But nothing in the universe lasts forever. Eventually, even a star must face the limits of what it can burn. For small stars like our sun, that ending is graceful. They expand into red giants, shed their outer layers into glowing shells of gas, and drift into quiet white embers. But for the giants, those at least 8 times the mass of our sun, the ending is anything but gentle. Inside their cores, the fusion furnace climbs the periodic ladder, fusing carbon, oxygen, and silicon until it reaches an element that refuses to play along. Iron. Iron is strange. It marks a boundary in the universe's energy economy. Up to that point, fusion gives energy. Each new element formed releases light and heat, but forging iron costs more energy than it returns. When a star's core fills with iron, its heart turns cold. There is no more fire to push back against gravity. At first, the change is subtle, a slight imbalance, a tremor deep inside. Then, in less than a single second, the entire core collapses. Imagine something as large as the sun shrinking faster than a blink, faster than thought. The pressure grows beyond comprehension. Electrons are forced into protons, merging to form neutrons. A flood of ghost-like particles called neutrinos bursts outward, carrying away much of the core's remaining energy. The outer layers, no longer supported by radiation, rush inward, strike the suddenly rigid neutron core and rebound with unimaginable violence. That rebound, amplified by the storm of neutrinos streaming outward, tears the star apart. From light years away, we see the result as a supernova, a single brilliant flash outshining an entire galaxy for a few fleeting weeks. It is the loudest silence in nature, a star ending not in darkness, but in one final blaze of generosity. In that explosion, the universe is enriched. The calcium in your bones, the iron in your blood, the gold in your ring, all forged in that chaos, scattered across space to seed new worlds. And at the centre of it all, what remains is a paradox. The smallest, heaviest thing nature can make. A neutron star. Picture it. The mass of our sun compressed into a sphere barely 20 kilometres wide, about the size of a city. A spoonful of its matter would outweigh mountains, perhaps 1 billion tons in a single taste. Yet if you could somehow stand upon its surface, it would seem utterly still. No flames, no crackling fire. Just a dark, solid crust glowing faintly with the memory of its birth. There's a kind of peace in that image. The violence is over, the noise has passed. All that remains is density, order, and the quiet hum of gravity. The star's heart has collapsed, but not into despair, into persistence. It continues, transformed, obeying a different kind of balance now. Where fusion once held gravity at bay, a new force has taken over. The stubbornness of matter itself. The pressure that arises when particles are squeezed so tightly, they simply refuse to share the same space. This is where the story of the neutron star truly begins. A world so dense that it bends light, so small that it hides in plain sight, so ancient that its heartbeat may outlast the galaxies around it. But before we reach the heart of that mystery, let's rest a moment at the edge of the explosion, where the light of a dying star fades into silence, and the first quiet pulse of something new begins to form. If you could watch the end of a massive star unfold, you would see calm turn to catastrophe in less than the time it takes to blink. For millions of years, the star has burned in balance, fusing one element into another, glowing steadily against the darkness. Then, in a heartbeat that lasts less than a single second, everything changes. The quiet equilibrium shatters and gravity wins. At first, the collapse begins deep inside, invisible from the surface. The iron core, once the heart of fusion, can no longer produce energy to push outward. Without that pressure, the immense weight of the outer layers begins to crush inward, falling toward the centre at speeds close to 1/4 of the speed of light. It is a silent implosion, yet within that silence, physics itself begins to twist. The density rises beyond imagination. Electrons are forced into protons, a process scientists call electron capture. But we can think of it more simply. It's as if matter folds in on itself. The protons and electrons combine to form neutrons, tiny neutral particles that pack tightly together like grains of sand in a clenched fist. In that moment, a flood of ghostly particles called neutrinos bursts outward, billions of trillions of them, carrying away much of the star's energy. These neutrinos are so elusive that they can pass through entire planets without hitting a single atom. Yet, in this brief instant, they carry the roar of the dying star's heart. Imagine standing, if standing were possible, near that collapsing core. You would feel gravity multiply 100 billion times over. A marble dropped there would hit the surface at nearly half the speed of light. Time itself would feel heavy, stretching and slowing as gravity deepened its grip. But before you could even process the thought, it would already be over. When the core finally becomes too dense to compress further, the collapse halts abruptly. The neutrons resist being squeezed any closer together. It's like trying to press one mountain into another. There's no more room to give. That sudden stop sends a shockwave rushing outward through the infalling layers. The shock travels faster than any sound, faster than comprehension, blasting through the star's body like a rebounding echo of its own death. For a brief moment, the shock stalls, its energy drained by the collapsing matter above it. But then, the escaping neutrinos, those silent messengers of the core, rush outward in unimaginable numbers. They strike the falling material, transferring their energy, reigniting the fading shock. It's a moment of defiance, the dying star pushing back one final time, and that push is enough. The shockwave surges outward again, tearing the star apart from within. The result is a supernova, one of the most powerful events the universe can create. For a few shining weeks, that single point of light can outshine the entire galaxy it belongs to. If you were to look at it through a telescope, it would appear as a star suddenly blooming in brightness, brighter than anything else in the sky, and then slowly fading as if exhaling its last breath. What you see is only the surface expression of an interior catastrophe, the moment when matter gives way to something new. In that explosion, the outer layers of the star are hurled into space, carrying with them the heavy elements forged in the furnace of fusion. Gold, silver, platinum, uranium, metals that will someday glint in rings, electronics, and distant planetary crusts are born in this single violent act. The universe, in its own way, recycles everything. Death in space is simply another word for renewal. But the heart that remains behind is another matter entirely. Beneath the explosion, inside what was once the star's shining centre, the new object is born, the neutron star. It's so small you could cross it in a car ride if only you could survive the gravity. But no one ever could. Its mass is nearly that of our sun, yet it's packed into a sphere barely 20 kilometres across. Think of a teaspoon filled with its material. It would weigh more than all the mountains on Earth combined. Even light finds it difficult to leave. The gravity there bends space so steeply that photons, the particles of light, curve back toward the surface. Only the most determined manage to escape, and even they crawl out redshifted and slowed, as if weary from the climb. If you could look at a neutron star close up, its light would appear tinted and soft, not because it's dying, but because time itself moves differently in its presence. Around that newborn remnant, the debris of the explosion still expands, vast clouds of gas and dust glowing in every colour, sculpted into ribbons and knots by magnetic fields. This is the aftermath we see from Earth centuries later, when we photograph nebulae like the Crab, the Veil, or Cassiopeia A, each one the ghost of a supernova long past, still breathing faintly in the vacuum. The core at the centre of each, tiny and invisible to the eye, spins silently, like a cosmic heart that refuses to stop beating. Some neutron stars are quiet, fading embers in the dark. Others spin so rapidly that they flash like lighthouses, pulsars sending rhythmic signals across the universe. Some are wrapped in magnetic fields 1 trillion times stronger than Earth's, capable of tearing atoms apart. And some, when paired with another star, will eventually spiral together again, merging in a final burst that creates even heavier elements and ripples the fabric of space-time itself. But all of that lies ahead. For now, we're standing at the threshold, the exact moment when destruction gives birth to persistence, when collapse becomes stability. The star is gone, but something new has taken its place. A fragment of its core that defies intuition, a monument to the laws of nature pressed to their limits. It is smaller than a city, denser than anything we can imagine, and older in its silence than we will ever be. If you listen closely, you can almost feel its stillness, an echo of the explosion that created it, reverberating softly across time. The light has faded, the dust drifts outward, and at the centre of it all the neutron star waits, cooling, spinning, and holding the memory of a sun that once was. When the light of the supernova finally fades, what's left behind would hardly seem like the heart of such a magnificent event. If you could drift through the expanding cloud of gas and dust, you would find, floating in the centre, something no bigger than a city, quiet, solid, and impossibly dense. It doesn't burn or shine in any ordinary way. It simply exists, holding more matter in its small form than the human mind can easily hold in thought. This is a neutron star, the smallest and heaviest thing nature knows how to make without letting it collapse into a black hole. It is the leftover core of a star that once blazed millions of times brighter than our sun. Now, all that light and fury have been reduced to silence and weight. Let's try to imagine it, not in numbers, but in feeling. Picture a sphere about 20 kilometers across. That's the distance you might drive from one side of a city to the other. Now imagine squeezing the entire mass of our sun into that space. The atoms that once danced freely in solar plasma are now crushed until the spaces between their particles have vanished. The nuclei are packed so tightly together that even the subatomic structure starts to blur. Matter has been pushed to the edge of what matter can be. If you could take just 1 teaspoon of this substance, about 5 cubic centimeters, it would weigh roughly 1 billion tons, more than every building, every ship, every mountain on Earth combined. And yet, despite this extraordinary density, the neutron star holds itself together, balanced by a quiet and invisible resistance known as degeneracy pressure. It isn't pressure in the everyday sense. Nothing is pushing, nothing is straining. It's more like the natural stubbornness of particles that refuse to occupy the same space. Physicists sometimes call it the Pauli exclusion principle, but we can think of it more gently, the universe's most polite rule. Even at the smallest scales, every particle insists on its own identity, its own small pocket of existence. When gravity tries to crush them all into one point, they resist by simply saying, "No closer." That collective refusal is what holds up a neutron star. If you could look beneath its surface, the structure would unfold in strange layers. The outermost few meters form a crust of solid iron and other heavy elements, atoms stretched and flattened by gravity's pull, locked in a rigid lattice. Beneath that, things become even stranger. The nuclei are squeezed so tightly that they merge into exotic patterns, long tubes, thin sheets, and twisted filaments of matter that scientists whimsically call nuclear pasta. It's as if the star's crust has melted into an abstract sculpture, dense enough to stop a bullet made of light. Deeper, down lies the outer core where the neutrons flow freely, no longer bound into atoms. Here, matter behaves like a liquid metal ocean, a sea of neutrons laced with a few protons and electrons. This is no ordinary fluid, it's a superfluid, a state where friction disappears completely. If you were to set it swirling, it could keep spinning for millions of years without ever slowing down. Within that same layer, protons may move as a superconducting current, carrying magnetic fields that can wrap the entire star in invisible loops of power. At the very centre lies the great uncertainty, the inner core. We don't yet know exactly what it contains. It may be an even denser form of matter, where neutrons dissolve into their constituent parts. Quarks, those tiniest building blocks of everything we know. Or it could host stranger particles still, things that only exist under these extremes. Some physicists call it quark matter, others imagine hyperons, or even entirely new forms that combine characteristics of both. The truth is, no one has ever seen this region directly. It remains a mystery hidden inside an object no telescope can truly reveal. Still, we can infer a few things from the mathematics of balance. If the neutron star were just a little heavier, say, beyond twice the mass of our Sun, then even the pressure from its neutrons would no longer be enough to support it. Gravity would crush it further, collapsing it into a black hole. That upper limit, known as the Tolman-Oppenheimer-Volkoff limit, marks the boundary between what can stand and what must fall. It's a cosmic line between visibility and disappearance. Within that narrow window of stability, the neutron star exists in perfect equilibrium. Its gravity tries to pull everything inward, its quantum structure resists. The two forces hold each other in check, and the result is something unlike anything else in the universe. A sphere so dense that a single sugar cube of it would outweigh Mount Everest, yet so delicate that a single extra layer of matter could make it vanish into nothingness. If you were to stand on the surface of this star, though of course nothing could survive it, you would weigh 100 billion times more than you do on Earth. Your feet would sink instantly, your atoms torn apart by the difference in pull between head and heel. Even light, which usually travels in straight lines, would curve noticeably before escaping. And if you were to drop an object, a coin perhaps, it would reach the surface in less than a millisecond, striking with such force that it would release more energy than a nuclear bomb. And yet, in all this unimaginable violence, there is a strange kind of peace. The neutron star doesn't change much over time. Its surface cools slowly, radiating the last of its stored heat into the void. Its shape remains nearly perfect, a flawless sphere slightly flattened at the poles if it spins. Its gravity, while monstrous, is constant. In the stillness of the vacuum it simply endures, neither collapsing further nor expanding. To gaze upon it, if you could, would be to see matter in its purest and most stubborn form. No fire, no fusion, no motion, just weight and time locked together. The energy that once held galaxies in awe now fits inside something smaller than a mountain. It is both an ending and a beginning, the moment when nature stops shouting and starts whispering, when light gives way to gravity's quiet persistence. And somewhere inside that dense, unyielding shell, a new kind of order begins to emerge, a pulse, a rhythm, a hint of rotation. Even in its stillness, the neutron star remembers how to spin. Soon, that motion will reveal itself in the dark, flashing like a heartbeat through the cosmos. But for now, it simply waits, silent and perfect, suspended between gravity and grace. If you could somehow hold a neutron star in your imagination and peel it open, layer by layer, it would feel like descending through levels of impossible matter. Each step inward would reveal a new kind of physics, stranger and denser than the last. What looks from afar like a quiet grey sphere would turn out to be one of the most complex structures in the universe, an entire world compressed into a few dozen kilometers. Let's begin at the edge, where light escapes with effort. The surface of a neutron star is not solid in the way a planet's crust is solid, nor gaseous like the sun's surface. It is a skin only a few centimeters thick, made of atoms stripped bare and packed into a lattice so rigid it could hold mountains made of metal. If you brushed your hand across it, which of course you never could, it would feel perfectly smooth, smoother than glass, yet strong enough that a bump only a millimeter high would weigh as much as a mountain range. Beneath that thin surface lies the outer crust. Here, pressure forces atoms so close together that their electrons are squeezed free. What remains are bare atomic nuclei arranged in crystalline patterns, an immense grid of positive charges surrounded by a sea of drifting electrons. The deeper you go, the heavier those nuclei become, turning from iron into exotic elements that cannot exist anywhere else. The matter there behaves more like a metal than a rock, carrying electric currents with ease. As you move further inward, the pressure grows by staggering amounts. At a depth of just a kilometer, the density has already climbed beyond anything on Earth, hundreds of millions of tons packed into a space the size of a thimble. The nuclei now sit shoulder to shoulder, their boundaries blurring. Neutrons begin to leak out and drift freely between them, forming a kind of fog. You've reached what scientists call the inner crust, and this is where the universe starts to play with geometry. In this layer, matter takes on shapes with names borrowed from the kitchen: long rods, flat sheets, tangled webs. It's not whimsy. These are real structures formed by the competing forces of attraction and repulsion between particles. Researchers call them nuclear pasta, because the patterns resemble spaghetti, lasagna and gnocchi, though made not of flour but of atomic nuclei. They're among the strongest materials known, possibly 1 billion times harder than steel. If an earthquake could shake such a crust, the energy would ripple out as powerful bursts of radiation instead of sound. Sink another few kilometers and the structure changes again. The nuclei dissolve entirely, leaving a fluid made mostly of neutrons, with just a sprinkling of protons and electrons. This is the outer core, and it behaves like nothing in our everyday world. The neutrons here act collectively. They flow together in perfect coordination, like dancers who never miss a step. This is what scientists call a superfluid, a liquid that can flow forever without friction, without losing energy. If it begins to spin, it will keep spinning for millions of years because there is nothing inside it to slow it down. Alongside that superfluid sea, the protons form their own community. They pair up into currents that move without resistance, creating a superconducting state. These two phenomena, superfluidity and superconductivity, are not just curiosities. Together they generate magnetic fields, guide heat flow, and govern how the star's rotation evolves over time. The result is a body that is both incredibly rigid and incredibly fluid, a contradiction only the universe could sustain. And then, deeper still, you reach the inner core, the most mysterious region of all. Here, the pressure becomes so extreme that the distinction between individual neutrons may vanish. The neutrons could dissolve into their smaller components, quarks, turning the heart of the star into a dense soup of fundamental particles. Others think the core might harbour hyperons, particles containing strange quarks that exist only under these conditions. There are even bolder theories proposing that a neutron star might transform into something entirely new, a quark star made purely of quark matter. No one knows for sure. These possibilities remain mathematical whispers, glimpsed only through computer models and the indirect evidence of what we observe from afar. Every telescope measurement, every recorded pulse and gravitational wave is a small clue trying to tell us what lies within. To open a neutron star physically would be to destroy it. So we study the echoes instead, the slight variations in its spin, the faint changes in its radiation, as if listening to a heartbeat through many layers of silence. Even without certainty, what we do understand is awe-inspiring. The outer layers, just a few kilometers thick, might weigh more than all the stars in our solar neighborhood combined. The core, though only a fraction of the star's volume, holds almost all its mass. Inside it, the densities climb to a level where a single teaspoon of material could outweigh Mount Everest 1 billion times over. And yet, within this crushing pressure, matter arranges itself into orderly patterns, flowing and humming in ways that suggest grace rather than chaos. Some scientists describe the inner structure as a frozen symphony. The particles interact in repeating waves, creating vibrations that can travel through the star like sound through a bell. When we observe slight changes in timing from pulsars, the rhythmic neutron stars that send steady signals across space, those tiny shifts might be the result of quakes deep in this hidden world. It's as though we're listening to the music of an object far too dense to see, decoding its melody one note at a time. From the surface to the centre, the story of a neutron star is one of compression and transformation. Ordinary matter, gas, plasma, atoms, collapses into something extraordinary, yet never quite loses its ability to organise, to structure itself. Even at the brink of destruction, the universe prefers elegance. It creates order from pressure, harmony from collapse. And when you think about it, that's a lesson hidden in the physics. The neutron star is not chaos frozen, its resilience condensed. Every layer, from the smooth crust to the superfluid core, is the universe's way of saying that even under impossible strain, beauty can persist. If you listen quietly, you might almost imagine the hum of that hidden interior, a soft vibration, like the lowest note in a song that never ends. Somewhere in that depth, motion is already stirring. The star may be small, but it still remembers the momentum of its birth. Soon, it will begin to turn, slowly at first, then faster, until its surface moves at a fraction of the speed of the light. And when it does, this dense relic will no longer be just a remnant. It will become a beacon. The next chapter of its life will not be silent, but rhythmic, echoing across the cosmos like a pulse that refuses to fade. If gravity on Earth is the feeling that keeps you grounded, then gravity on a neutron star is something altogether different. It doesn't just hold you to the surface, it pulls at you with such ferocity that the very idea of standing becomes meaningless. On Earth, gravity feels gentle, like a steady hand resting on your shoulder. On a neutron star, that hand would become an unrelenting fist, pressing with a force 100 billion times stronger. To imagine it, start small. Here, a dropped ball falls to the ground at roughly 10 meters per second each second, a pace your mind can easily picture. Now imagine that same motion multiplied beyond comprehension. If you dropped a pebble from your hand on a neutron star, it would strike the surface almost instantly, moving at close to half the speed of light. The energy released would be enough to vaporize the rock, the hand that held it, and the air around it, if such air could exist. But the most extraordinary part isn't how quickly things fall, it's that down itself begins to change. Gravity here doesn't just pull on matter, it pulls on space, on time, on light itself. The closer you move to the surface, the more the fabric of reality curves around you. Space bends, time slows, and the very idea of a straight line becomes impossible. If you could float safely above a neutron star, you would find that every direction leads inward. The horizon would wrap strangely, showing you parts of the surface that should be hidden behind the curve. The star's gravity is so strong that light, which normally travels in perfect straightness, now follows paths that curl. Photons, those tiny messengers of illumination, have to climb uphill to escape. Many never make it. The light that does emerge comes out weakened and redshifted, its energy drained by the climb through warped space-time. This isn't poetic exaggeration. It's a literal bending of the universe. Even Einstein's equations, beautiful as they are, seem to tremble under such extremes. The mathematics that describes this place tells us that time itself flows differently here. If you had two clocks, one resting near the surface of a neutron star and another far away, they would quickly fall out of sync. The one near the surface would tick slower, its seconds stretched longer by gravity's grip. To put it gently, a moment spent near a neutron star would feel normal to you while you're there, but to someone watching from far away, it would look as if you were moving in slow motion. A second for you might be 2, 3, or 4 seconds for them, depending on how close you stand. This is called gravitational time dilation, a quiet reminder that even time itself is not constant. It breathes with the pull of gravity, expanding and contracting like lungs inhaling eternity. Light, too, experiences this distortion. If a beam of light leaves the surface of a neutron star, it loses energy as it climbs away, trading brightness for survival. Its colour shifts toward the red, the same way sunset light reddens as it scatters through the atmosphere. But here, the shift is not caused by air, but by gravity itself. The result is a faint crimson glow that carries the last warmth of the explosion that birthed it. In this place, there's no simple line between physics and philosophy. What does it mean for time to slow? For light to struggle against existence? If you were standing on the surface, your weight would be unimaginable. A human body would be crushed flat, its atoms torn apart by the difference in pull between head and feet. Even steel would behave like soft clay. Yet, in that same environment, the neutron star remains perfectly steady, balanced between collapse and resistance, an object so extreme it defies destruction by simply existing. If the neutron star spins, and most of them do, things become even stranger. At the equator, the surface can move at thousands of kilometers per second. That motion slightly counters gravity, making the star flatten just a little, like a spinning top. From a distance, it may appear perfectly spherical, but in reality it bulges ever so slightly at the waist. This delicate shape is another expression of balance. Gravity pulling inward, rotation stretching outward, both agreeing on a fragile truce. The space around it doesn't stay still either. As the star spins, it drags the very fabric of space-time along with it. This phenomenon, called frame dragging, means that even emptiness is not free here. If you tried to hover nearby, you'd find yourself slowly pulled into rotation, carried along by the twisted geometry of the star's gravity. It's as if space itself can't resist joining the dance. We sometimes imagine black holes as the ultimate demonstration of gravity's power, but neutron stars are just shy of that threshold. They are the last possible form of matter before gravity consumes itself completely. If a neutron star were even a little heavier, just a few tenths more the mass of our Sun, it would no longer be able to support its own weight. It would collapse beyond its limit, and not even light would escape. In that sense, neutron stars are nature's last defiance before darkness, and yet from a great distance they appear peaceful. Their gravity is invisible unless you look for its effects. The bending of light, the slowing of time, the way nearby stars seem to orbit an emptiness that isn't truly empty. Astronomers can sometimes spot these distortions through careful measurements, tracing the way light curves as it passes by. In those observations, we see gravity not as a force but as a shape, a gentle dent in the cosmic fabric, carved by something impossibly dense. When you think about it this way, a neutron star isn't simply an object. It's a place where the universe behaves differently, where the usual rules pause to take a breath. Gravity stops being just a pull and becomes a sculptor, shaping not only matter, but also the flow of time and the path of light. If you were to hover far enough away to see the whole sphere, it might appear to shimmer slightly, its outlines softened by the bending of light. You would never quite see the far side, because gravity keeps revealing it to you. The star shows more of itself than it should, like a mirror folding its own reflection. What looks calm from afar is actually a storm of geometry, space and time intertwined, and yet it is utterly silent. No wind, no tremor, no motion, just gravity's endless patience, holding everything in place. Every atom inside that star, every photon trying to escape, every tick of a clock nearby is a participant in that stillness. Down is no longer a direction. It is a destiny, a call inward that never ends. The neutron star doesn't pull things down in the way Earth does. Instead, it bends everything, space, light, time, toward its center. Down here means toward forever. And somehow, within that inward pull, the star holds its shape, resisting complete surrender. It's the quiet equilibrium between the urge to collapse and the will to endure. In that balance, the neutron star becomes more than an object. It becomes a lesson in gravity's poetry, a reminder that even the strongest forces in the cosmos can find peace, that even time itself can slow enough to rest. If you could watch a neutron star from a safe distance, perhaps orbiting it in a small capsule that floats on the edge of its gravity, you would begin to notice something subtle but extraordinary. The clocks inside your ship would not agree with those you left behind on Earth. Every tick near this dense star would stretch slightly longer, as if time itself were caught in a slow, deliberate breath. The closer you drift, the stronger this effect becomes. It isn't that your clock is broken or that space is playing tricks. It's that time, the most familiar rhythm we know, isn't a universal beat at all. It changes its pace depending on how deep it sits in gravity's well. Around a neutron star, that well is unimaginably deep. From far away, the seconds seem to stretch like soft taffy. You might think you've been circling the star for just a few minutes, yet by the time you return to the wider universe, entire hours could have passed. To the rest of the cosmos, you moved in slow motion, but to you everything felt normal. Your heartbeat, your breathing, the ticking of your onboard watch, all perfectly in sync. This is one of the quietest and most beautiful truths Einstein's theory of relativity ever revealed. That time is not an even river but a landscape, rising and falling like hills and valleys. Gravity is the sculptor that shapes it. The stronger the gravity, the slower time flows. On Earth, the difference between your head and your feet is measurable but minuscule. Your head ages a tiny fraction faster because it's slightly farther from the planet's centre. But near a neutron star, the difference becomes breathtaking. A person standing at the surface, if such a thing were possible, would experience time moving far slower than a person just a few kilometres above. If you could somehow watch a nearby clock on the star's surface, it would appear to tick lazily, as though resisting the flow of the universe. The sound of each second would arrive stretched and softened, like an echo travelling through thick air. Light too would feel this drag. Every photon that escapes the surface would emerge dimmer and redder than when it began its journey, its colour shifted by gravity's insistence on slowing time and space alike. And yet, this is not distortion in the way a mirror warps an image. It's something gentler, more intricate. The bending of time is smooth and continuous, following the same logic that holds planets in orbit and shapes the paths of falling stones. In a way, the universe keeps perfect harmony. It's just that each place sings its own tempo. Imagine for a moment that you could drop two identical clocks, one to hover far from the neutron star, another lowered just above its surface. To the distant observer, the lower clock seems sluggish, its seconds dragging endlessly. But if you asked the lower clock, it would swear that it's ticking exactly as it should. That's the magic of relativity. Every viewpoint is correct within its own frame, even if those frames disagree. This stretching of time is not only a curiosity, it's something we can measure. Astronauts aboard satellites orbiting Earth already account for it. The time aboard their instruments flows ever so slightly faster than it does down here on the ground. If engineers didn't correct for that difference, our global positioning systems would drift, and the maps on your phone would slowly lose their way. Here, near the mild gravity of Earth, that correction amounts to mere billionths of a second. Near a neutron star, the correction would be so great that without it, meaning itself would blur. Now imagine living on a world orbiting such a star. The sky would appear warped, with light from distant stars bending into arcs around the dense object. As the neutron star rotates, beams of radiation might sweep across the heavens like lighthouse beams, illuminating your world in rhythmic flashes. Each pulse would arrive slightly redder than the last, each one carrying within it the faint signature of slowed time. And somewhere far across the galaxy, another observer might receive those pulses and use them as a clock, measuring the universe's expansion, tracking gravitational waves, listening for the slow beating heart of matter itself. They would never see your world directly, but through those pulses they would know it existed, locked in an orbit where time itself flows differently. When we talk about these effects, it's easy to fall into numbers, percentages of time dilation, gravitational potentials, equations that fit neatly on chalkboards. But none of that captures the experience. The real wonder lies in imagining what it feels like. Time itself, the thing we trust most, becomes fluid. Seconds stretch and curl. Light bends. Motion changes meaning. The universe, in its quiet way, becomes elastic. There's something poetic about that flexibility. It means that reality is not brittle. It adapts. Even under unimaginable weight, space and time do not shatter. They simply reshape. The neutron star, in this sense, is not a place of chaos but of deep balance. Gravity presses and time responds, slowing just enough to keep the equation true. It's the cosmos maintaining its own rhythm, even when that rhythm is slower than any metronome could mark. If you could stand above the neutron star and look outward, you might see the universe racing ahead, the galaxies would appear to age faster, their light flickering at a quicker pace. But, in truth, it's your own clock that has changed, your perception that has narrowed. It's a humbling reminder that fast and slow are not properties of the cosmos, but of where you happen to stand within it. As your ship drifts back outward, away from the dense gravity, you'd feel the invisible tension release. The seconds begin to regain their familiar cadence. Light brightens, colours sharpen. You return to the tempo of the wider universe, carrying with you the quiet awareness that time too has a texture. It can stretch and relax just like the fabric of space it lives within. And as you leave, the neutron star continues on, indifferent to your visit. Its gravity remains absolute, its time forever slow. The photons escaping its surface still climb upward, weary but persistent. Each carries a little story of resistance, a memory of the struggle to rise from a place where even time itself had to rest. In the silence of that distant world, you realize that slowness isn't a flaw. It's a kind of patience. The neutron star is what happens when the universe takes a deep breath and holds it, suspending motion, folding time, and waiting. And somehow, that waiting feels eternal, not because time has stopped, but because it has forgotten how to hurry. Far out in the quiet darkness, there are stars that refuse to stop spinning. Long after their explosions fade, after the dust and light of their deaths have drifted away, something within them keeps moving, an echo of the energy they once held. These are the pulsars, the universe's lighthouses turning endlessly in the dark. When a massive star collapses into a neutron star, it shrinks to a fraction of its former size. But the spin it had before doesn't disappear, it concentrates. The same way a dancer spins faster when pulling in their arms, a collapsing star speeds up as it becomes smaller. Its rotation, once a few times per month or per week, now becomes hundreds of turns every second. Imagine a sphere 20 kilometers wide spinning so fast that a point on its surface moves at 1/10 of the speed of light, yet remaining perfectly stable. This rapid spin would go unnoticed if it weren't for one small imperfection: the magnetic field. In a perfect universe, the magnetic poles and the axis of rotation would align, and no light would ever escape in a pattern. But nature loves small asymmetries. The magnetic poles of a neutron star are slightly tilted, so the radiation they produce shoots out in narrow beams. Two cones of energy that sweep through space like the beams of a lighthouse. Every time one of these beams crosses Earth, our telescopes pick up a brief pulse of radio waves, X-rays, or even visible light. To us, it seems like the star is blinking, on, off, on again. But the light never stops. It's simply rotating away and back again, a cosmic heartbeat with perfect rhythm. Some of these pulses are so regular that they make the most precise clocks known in the universe. While our atomic clocks on Earth may drift by a second over millions of years, some pulsars keep better time than that, never missing a beat. In 1967, a graduate student named Jocelyn Bell Burnell noticed something strange on her radio telescope's recordings. Tiny repeating blips appearing every 1.3 seconds. They were too regular to be natural noise and too steady to be man-made interference. For a while, the team jokingly labelled the source LGM, Little Green Men, because it seemed almost deliberate. But soon they found other sources across the sky, all pulsing in their own perfect tempos. It wasn't aliens, it was nature, discovering a new way to speak. Jocelyn Bell Burnell had found the first pulsar. Today we know thousands of them, scattered throughout our galaxy and beyond. Each one spins at its own rate, some slower, a pulse every few seconds, others unbelievably fast, hundreds or even thousands of pulses per second. The fastest of these are called millisecond pulsars, tiny neutron stars that have been spun up by pulling material from a companion star, stealing its angular momentum. It's as if, in their old age, these dead stars have found a way to dance again. The light from a pulsar isn't gentle light. It's radiation focused into narrow streams, compressed by the star's magnetic fields. Those fields can be 1,000,000,000,000 times stronger than Earth's, twisting and funneling particles into jets that race outward. The pulses we receive are the faintest remnants of those streams, a whisper from something far too powerful for us to touch. Yet their precision is astounding. Some pulses are so regular that we use them to test the stability of space-time itself. When their rhythm changes by even a millionth of a second, scientists know that something massive, perhaps a passing gravitational wave or a shift deep inside the star, has disturbed their internal balance. Each pulse we receive has travelled for thousands, sometimes millions of years before reaching us. By the time the signal flickers across a telescope dish, the neutron star that sent it might have slowed slightly, cooled, or even stopped. But the pulse still arrives, faithful to its pattern, a heartbeat long after the heart itself has changed. Listening to these pulses is like hearing the echo of a sound that began before life on Earth existed. If you could stand on the surface of a pulsar, though such a thing is beyond imagination, you'd see the magnetic field as a forest of invisible lines, curving outward from the poles and stretching far into space. Charged particles spiral along these lines at nearly the speed of light, producing radiation as they go. Each rotation sends a flash across the cosmos, a message written in magnetism and motion. To the universe, these pulses are tiny. To us, they are monumental. There's something quietly poetic about a star measuring time. On Earth, we built sundials, clocks, and atomic oscillators to keep order. But in the vastness of space, the cosmos keeps its own calendar through these rotating remnants. Their rhythms outlast civilizations, even galaxies. They are timekeepers for eternity. Astronomers use networks of pulsars to form what's called a pulsar timing array. By studying small deviations in their pulses, they can detect the faint tremors of gravitational waves passing between stars, ripples in space-time caused by colliding black holes billions of light years away. In this way, pulsars become instruments of cosmic listening. They turn from relics of death into tools of discovery, and yet, for all their precision, pulsars aren't entirely steady. Sometimes they hiccup. The reason lies within their strange interiors, superfluid cores that spin in perfect silence beneath a crust of rigid iron. Every so often, something deep inside shifts. A tiny crack forms, or a pocket of superfluid suddenly transfers its motion to the crust. The star speeds up just a little, for reasons we can only guess. Scientists call these events glitches, but they're not flaws. They're the neutron star's way of adjusting, of finding its rhythm again. Even in these irregularities, there's beauty. A pulsar doesn't simply fade into stillness. It ages gracefully, slowing little by little, giving its energy away to the space around it. Each turn costs it a fraction of its stored power, and over millions of years the spin winds down. Some will eventually stop, becoming dark spheres, invisible but still immense. Others will live longer, finding new partners, stealing momentum, and beginning the dance anew. When we look up and see a pulsar, we're seeing persistence made visible. These stars no longer burn with fusion. They shine by memory, by motion and magnetism alone. Every pulse is both a reminder of their death and a declaration of their endurance. They don't measure seconds for us. They measure the life of galaxies, and if you listen long enough, through the static and the silence, you might sense the quiet comfort in that idea, that somewhere out there the universe still keeps time ticking patiently in the dark. Even the most perfect rhythms in the universe sometimes stumble. For all their precision, pulsars are not metronomes made of metal and gears. They are living remnants of stars, complex and restless beneath their calm exterior. Every pulse that reaches us carries not only the story of their rotation, but also the subtle tremors of the dense matter within them, and sometimes that steady pulse slips, ever so slightly, out of time. Astronomers call these events glitches. They sound small, like a skipped beat in a song, but what they represent is astonishing. A pulsar that spins hundreds of times per second may suddenly begin spinning a little faster, perhaps 1 part in a million quicker than before. To us, the difference is almost invisible. But on the scale of a neutron star, it's seismic. It's as if the entire core, containing more mass than our Sun, momentarily shuddered and shifted its rhythm. The cause of these glitches lies deep beneath the crust, in the layers we can only imagine. Inside a pulsar, the outer shell is rigid, so strong that a mountain only a few millimeters high would weigh more than Mount Everest. Beneath that crust, however, lies the superfluid sea, neutrons that move in perfect synchrony, without friction, without slowing. This superfluid doesn't always turn at the same speed as the crust above it. Over time, a small difference builds up, a tension between two worlds spinning at slightly different tempos. Eventually something gives. The crust cracks, or the superfluid suddenly transfers some of its motion to the outer layer. It's a jolt, a moment of internal realignment. The entire star seems to lurch, and its spin increases just a fraction. Imagine a vast frozen lake under pressure. For years it looks perfectly still. Then one day, with a sound like a deep sigh, the ice shifts, releasing stored energy through a network of hidden cracks. That's what happens when a pulsar glitches. To detect such an event from Earth requires patience and precision. Scientists measure the timing of pulses that arrive from these distant stars with incredible accuracy, sometimes down to millionths of a second. When the rhythm changes, even slightly, it's recorded. A pulsar halfway across the galaxy might send a pulse every 10th of a second, so consistent that it could guide a spacecraft. Then, one night, its signal arrives a few microseconds early. Something has changed inside that spinning core. Somewhere a crack has whispered through the star's crust, and for an instant the cosmos skipped a beat. There are other moments, rarer still, when the opposite occurs, an anti-glitch. Instead of speeding up, the pulsar slows abruptly. The mechanism behind this remains uncertain. Perhaps it's the superfluid temporarily decoupling from the crust, dragging the rotation down instead of speeding it up. Or perhaps it's the star's magnetic field exerting sudden resistance, like a brake applied in silence. Whatever the cause, these small irregularities remind us that even perfection must flex. The discovery of glitches has given astronomers a way to glimpse the unseen interior of neutron stars. Each tiny change in spin is like an X-ray of their hidden structure, revealing how the layers interact under unimaginable stress. The patterns we observe tell us that the crust is elastic but fragile, that the superfluid beneath it carries most of the star's angular momentum, and that the boundary between them behaves like a frozen ocean locked against its surface. There's something humbling about watching a pulse so steady you could set your clock by it, and then realizing that even it can falter. But rather than diminish the beauty of pulsars, these imperfections make them more human, more relatable. They are reminders that even in the pure mechanics of the cosmos, there's room for error, adjustment, and recovery. When a glitch occurs, the star doesn't break. It simply finds a new rhythm. Its pulses continue, slightly altered, as if nothing happened. The new tempo remains steady, just a fraction quicker or slower. Over time, friction and magnetic braking will smooth things out again, returning the star to its slow, graceful decline. It's as if the universe allowed a moment of release, a deep breath before resuming its endless turn. For scientists, these moments are treasures. They reveal the dynamic life within matter so dense that our equations still struggle to describe it. Some teams monitor pulsars for decades, collecting pulse after pulse, looking for the faintest deviations. The data piles up like a diary of cosmic motion, each glitch a line written in the language of gravity and quantum mechanics. These observations help refine our understanding of how nuclear matter behaves when pushed to its absolute limits, something no laboratory on Earth could ever reproduce. But beyond the science, There's an emotional truth to these irregularities. To listen to a pulsar glitch is to hear a reminder that even the universe's most consistent patterns can change, and that the change itself is part of the order. Nothing in existence stays perfectly still. Every system, every heartbeat, every orbit carries within it the potential to shift. The pulsar's momentary stumble is not a flaw, it's a continuation of its story. If you could translate those pulses into sound, compressing thousands of radio beats into a rhythm you could hear, the glitch would sound like a skipped note, a tiny syncopation, followed by the return of perfect tempo. The music of the universe doesn't pause, it improvises. After each glitch, astronomers note how the pulsar slowly returns to its long-term slowdown, losing rotational energy as it emits radiation and magnetic waves into space. This process, known as spin-down, is how neutron stars age. Over millions of years, their rotation slows from hundreds of turns per second to only a few. Their pulses fade, their beams weaken, and they fall silent. But the silence isn't an end, it's simply another phase of rest. Not all neutron stars follow this quiet path. Some live louder, charged with magnetism so intense that it reshapes their entire being. In these stars, the gentle ticking of a pulsar gives way to a deeper, wilder rhythm, a symphony of magnetic storms. Their fields twist space itself, tearing open their crusts and flaring across galaxies. These are the magnetars, the loud cousins of pulsars, whose songs are less like heartbeats and more like thunderclaps. And so, from rhythm to rupture, from steady pulse to roaring storm, the story continues. Even the stars that seem most constant still change, and in their change, they reveal the restless creativity of the cosmos. What began as the simple ticking of time now grows into something grander, a melody of magnetism awaiting to be heard. Some stars end their lives quietly, fading into the dark with nothing but a whisper of radiation. Others, though, those with a particular kind of ferocity left over from their birth, refuse to go gently. Their gravity is immense, their spin rapid, but what truly defines them is their magnetism. These are the magnetars, neutron stars taken to the edge of reason. If a pulsar is a ticking clock, a magnetar is a storm wrapped in silence, an orchestra of power compressed into a sphere only 20 kilometers wide. To grasp how strange that is, imagine Earth's magnetic field, the invisible shield that guides compasses and shields us from solar winds. A magnetar's field is roughly 1 trillion times stronger. If you were somehow close enough to it, the field could erase the data on a credit card from halfway across the moon. It could pull the iron out of your blood at a distance of 1,000 kilometers. It is magnetism made tangible, terrifying, and almost beautiful. Where does such power come from? It begins in the chaos of birth. When a massive star collapses, its core not only shrinks but also spins faster. Magnetic fields that once wrapped the whole star are squeezed and intensified by this rotation, stretched and wound up until they roar. In most neutron stars, that field settles into balance, becoming the steady engine that drives pulsar beams. But in a few, the amplification runs wild. Their fields reach levels so high that they twist the fabric of the star's crust, creating tension that never quite relaxes. These are the magnetars, defined not by light, but by the invisible power flowing through them. Over time, that power cannot stay quiet. The magnetic field tries to straighten itself, to unwind the knots it created during the star's birth. But the crust resists, solid, stubborn, and incredibly strong. As stress builds, the crust eventually fractures. The result is a starquake, the stellar equivalent of an earthquake. Except the energy released isn't mechanical, it's electromagnetic. A burst of radiation, bright enough to outshine an entire galaxy for a few seconds, erupts from the surface. The magnetar screams, then falls silent again. These outbursts were first detected in the late 1970s, When satellites designed to watch for nuclear explosions around Earth picked up sudden flashes of gamma rays from deep space, they weren't bombs, they were something older and grander. One famous flare in March 1979 was so intense that it overloaded detectors, saturating them from a distance of more than 100,000 light-years. Another, in December 2004, was so powerful that it caused a brief ionization in Earth's upper atmosphere. For a fraction of a second, one of these dead stars changed the electrical state of an entire planet. After such a burst, the magnetar cools and calms. For years it may seem quiet, rotating slowly, its magnetic energy bleeding away little by little into the surrounding vacuum. Yet even in this calm, its field lines continue to twist. Some magnetars spin once every few seconds, slower than most pulsars, but their strength makes up for the lack of speed. The immense magnetic pressure acts like a brake, stealing the star's rotational energy and converting it into light and particles that stream into space. This is called magnetic braking, though the name hardly captures the elegance of the process. The star isn't struggling against friction, it's giving away energy, flinging part of itself outward. You could imagine it as a ballerina spinning so fast that her dress becomes lightning, her motion lighting up the room. Every turn releases a trace of that inner energy, each revolution a gift to the surrounding cosmos. And when the spin slows enough, the magnetic field has its say again, reshaping the crust, bending, storing tension for the next quake. The cycle repeats, sometimes decades apart, sometimes in quick succession. If you could observe a magnetar directly, which no human eye can, the sight would be otherworldly. The surface might glow faintly blue-white, streaked with invisible currents, the field lines looping outward like ribbons of glass. Around it would shimmer a halo of high-energy particles, dancing to rhythms that only the universe could hear. And yet, amid all this intensity, the magnetar would appear still. Its violence is inward, its movement hidden beneath layers of silence. Magnetars challenge everything we think we know about how matter behaves. Their magnetic fields are so strong that they distort atomic structures, stretching them into strange shapes, pulling electrons into elongated orbits. In laboratories on Earth, no experiment can recreate such conditions. The equations we use to describe them verge on poetry because the physics itself begins to blur. It's a reminder that the universe can go far beyond our comfort zones and still remain beautiful. Some theories suggest that magnetars may be responsible for one of the most mysterious phenomena in modern astronomy: fast radio bursts, or FRBs. These are millisecond-long flashes of radio energy that appear at random from distant galaxies, each one brighter than entire suns for the briefest moment. No one knows for certain what causes them, but magnetars, with their immense energy and magnetic instability, are prime suspects. In 2020, astronomers observed a magnetar in our own galaxy producing a burst eerily similar to these extragalactic signals. For the first time, it seemed the universe had whispered a clue. Despite their terrifying power, magnetars are short-lived compared to other neutron stars. Their magnetic fields decay over tens of thousands of years, bleeding energy until they settle into quiet retirement as ordinary pulsars or invisible cold remnants. Their lifespans, short on cosmic scales, are filled with brilliance and fury, a brief career of storms before the inevitable calm. And yet, what a career it is. When a magnetar flares, the energy released in a single second can equal what our sun emits in 100,000 years. The burst radiates in all directions, lighting up surrounding gas clouds, triggering afterglows of X-rays and radio waves that can last for weeks. Astronomers, watching from far away, can only marvel. These events are cosmic punctuation marks, moments when the universe raises its voice. If pulsars are the ticking clocks of creation, magnetars are its thunderclaps. They remind us that even death can produce power, that stillness can hide ferocity. Somewhere in the distant night, another flare may be building, its energy winding tighter and tighter, waiting for release. When it finally comes, it will light up half the galaxy for a heartbeat, then fade, leaving behind only the faint murmur of magnetism and the whisper of rotation. And after that, silence again, deep, immense, and somehow peaceful. For all their violence, magnetars eventually rest. Their fields weaken, their outbursts fade, and their energy disperses into the quiet. What remains is not destruction, but transformation. The conversion of chaos into harmony, energy into emptiness. They are, in the strangest way, the universe teaching itself how to let go. Deep inside a magnetar, there is a constant struggle, a quiet tension between the immense magnetic field that wants to reshape the star and the rigid crust that resists. It's a slow dance of pressure and restraint. For years, sometimes centuries, that tension builds invisibly. Then one day, in a fraction of a second, the magnetic field wins. The crust fractures, the star trembles, and what follows is one of the most violent displays of energy in the universe. From the outside, there's no warning. The magnetar spins, faintly glowing in X-rays, appearing calm. But inside, the magnetic field lines, those invisible threads that weave through and around the star, are twisting. They bend, reconnect, and stretch, storing energy like coiled springs. When they finally snap back into place, the stored energy explodes outward in a flare so bright that even from thousands of light years away, our instruments can feel it. To imagine it, think of Earth during an earthquake. The crust here breaks when stress between tectonic plates becomes too great, releasing energy in waves that ripple through rock and air. A magnetar quake is the same concept, but magnified beyond comprehension. The plates are made of nuclear matter, the densest solid surface known, and the energy release can equal what our sun emits in 100,000 years, all unleashed in the blink of an eye. When the field snaps, the outer layers of the magnetar crack like ice on a frozen lake, sending vibrations through its interior. These vibrations ring through the star like the tolling of a bell. The magnetic field disrupted flings particles outward, creating a flash of gamma rays and X-rays that races across the galaxy. For a brief moment, the magnetar outshines everything else nearby. Then, just as quickly, it fades, returning to silence as if nothing happened. The first time astronomers witnessed such a burst, they didn't know what to make of it. In March 1979, detectors aboard spacecraft suddenly recorded a flood of gamma rays, so powerful that it overwhelmed the instruments. The burst seemed to come from nowhere. Over time, similar events were seen again, one in 1998, another in 2004. The 2004 flare, from a magnetar in the constellation Sagittarius, was so intense that it briefly altered Earth's ionosphere, changing how radio waves bounced around our planet. A star halfway across the galaxy had for an instant touched our sky. When the gamma ray flash subsides, the magnetar often emits an afterglow, a slow fade of X-rays as its magnetic field settles back into place. The crust, though cracked, holds. The star does not disintegrate, it endures. The fractures may seal again as the material shifts and rehardens under the enormous pressure. The magnetar's heartbeat resumes, slower now, a little steadier. But deep within, the field is already rebuilding, coiling itself for the next flare. Some magnetars repeat this cycle, releasing smaller flares every few years. Others might erupt only once in millennia. Each event is unique, shaped by the star's mass, its magnetic field, and the geometry of its internal stresses. In a way, every magnetar has its own personality. Some are volatile, some restrained, some unpredictable. The cosmos is vast enough to hold them all. The magnetic field that drives these outbursts is not only powerful, it's complex. It threads through the crust and the core, interacting with superfluid layers of neutrons and superconducting protons. These currents don't simply flow, they shift and tangle in ways we can barely describe. When magnetic lines reconnect, they release bursts of energy just like solar flares, but magnified to cosmic proportions. The light we see is only the surface trace of those deeper rearrangements. For astronomers, studying these bursts is like eavesdropping on the inner workings of the universe. Every pulse of radiation carries information about the conditions that created it. The density of the crust, the strength of the magnetic field, the way matter behaves at extremes no laboratory could replicate. By watching how the flare brightens and fades, scientists can estimate how the field moved, how fast the crust responded, and how the star cooled afterward. In this way, even chaos becomes data. Recently, evidence has emerged linking magnetar flares to mysterious flashes called fast radio bursts. These are millisecond-long bursts of radio waves that appear unexpectedly across the sky. Their source is often far beyond our galaxy. Some repeat, some do not. For years, their origin was unknown. Then, in 2020, a magna in our own Milky Way produced a brief radio burst that looked strikingly similar to the extragalactic ones. It was the first real clue, a glimpse of a process that connects magnetism, matter and light across unimaginable distances. If these bursts truly come from magnetars, then each one is a whisper of a magnetic storm too distant to see directly. The radio waves travel for millions of years before reaching our telescopes, crossing empty space like faint heartbeats. When we detect them, we're listening to the echo of a field snapping in a star that may already be long gone. Yet for all their violence, magnetars are fleeting phenomena. Their extreme magnetic fields decay over time, bleeding away energy until they become ordinary neutron stars. In a few tens of thousands of years, an instant in cosmic history, their fury fades, their flares stop, and their spin slows. What remains is a quiet, stable remnant. The storms pass. The sea of space-time becomes still again. There's a strange peace in that knowledge. The magnetar, once fierce enough to shake entire galaxies, eventually learns to rest. Its power is not wasted. It becomes part of the interstellar medium, energy scattered into the cosmos, recycled into future stars and planets. In that sense, even its outbursts serve creation. The universe builds through destruction, shaping new worlds from the remnants of the old. When the field finally goes still, the magnetar doesn't vanish. It becomes invisible to our eyes, its magnetism spent, its heat fading into the cold of space. Somewhere out there, thousands of such quiet relics drift, reminders of storms long past. If we could listen carefully enough, perhaps we'd still hear the faint hum of their magnetic ghosts, the last trace of tension slowly unwinding. And so, the story of magnetars ends not with an explosion, but with a sigh. After years of twisting and snapping, of burning brighter than galaxies and then fading into darkness, they leave behind a lesson written in silence. Even the strongest forces in nature must one day relax. Power, like light, is meant to be released, not hoarded. The universe, vast and ancient, keeps teaching that same truth over and over through the lives and deaths of its stars. For most of human history, the universe was something we saw only through the light that reached our eyes. A faint glow of stars, a smear of colour from a distant nebula, that was all the cosmos would offer. But the neutron star, and its more magnetic kin, do not speak in visible light alone. They send their stories in radio waves, X-rays and gamma rays. Colours beyond what we can see, but not beyond what we can listen to. To understand these dead stars, humanity had to learn to see with more than sight. When astronomers study a neutron star, they use a collection of instruments scattered across Earth and space, each tuned to a different frequency of the universe's song. Radio telescopes, with their great white dishes, Listen for the rhythmic whispers of pulsars, the lighthouses ticking in radio time. X-ray observatories, orbiting above the atmosphere, watch the hot surfaces of magnetars, glowing faintly from the heat of their own stress. Gamma-ray detectors catch sudden outbursts, those brief cosmic shouts that mark a crustquake or magnetic snap. Together they form a symphony of observation, each instrument playing its part in translating silence into understanding. The Chandra X-ray Observatory, launched by NASA in 1999, was one of the first to give us a detailed portrait of these compact stars. Instead of seeing them as static points, Chandra revealed them as glowing orbs, sometimes surrounded by faint halos of gas. In its sharp vision, astronomers could trace how energy flowed from the star into the surrounding space, streams of high-energy particles twisting through magnetic fields. Then came XMM Newton from the European Space Agency, confirming that even after thousands of years, neutron stars still carry the thermal memory of their violent births, their surfaces cooling in slow motion. Closer to home, the NICER instrument, perched on the International Space Station, has become our most intimate listener. It measures X-rays from neutron stars with extraordinary precision, timing their arrival down to microseconds. From those tiny variations, scientists can infer the size and shape of the star itself, using geometry and light to reconstruct what no eye can see. It's as if NICER is running its fingers along the invisible surface of these dense objects, feeling their contours through the tremors of photons. Each wavelength tells a different story. The radio band reveals rotation, pulses of energy marking each spin. X-rays expose surface heat and magnetic storms, the afterglow of ancient violence. Gamma rays capture the briefest tempests, the instant when fields reconnect and explode. When combined, these layers give us a complete portrait. The rhythm, the heat, the outburst, the cooling. It's not unlike learning about a person by hearing their voice, watching their expression, and sensing their heartbeat, all at once. Sometimes the data doesn't come from light at all. Neutron stars are also laboratories for sound, not sound as we hear it, but vibrations in space-time itself. We call them gravitational waves, though ripples in existence might be closer to the truth. When neutron stars spin, their slight irregularities can send out faint, continuous tremors through the fabric of the universe. When they collide, those tremors become waves so strong they can travel for hundreds of millions of years. In 2017, a pair of neutron stars in a distant galaxy spiraled together and merged. The event, named Rebirth 7, was the first time humanity both saw and heard a cosmic collision. Gravitational wave detectors, two enormous L-shaped observatories called LIGO in the United States and Virgo in Europe, picked up the rhythmic stretching of space-time as the stars circled each other, their orbits tightening with every turn. A fraction of a second later, telescopes across the world caught the flash of light that followed, the brief, beautiful bloom of a kilonova. For the first time, we witnessed light and gravity speaking in harmony. That moment changed everything. It confirmed that neutron star mergers create heavy elements like gold and platinum. It showed that the universe's most violent acts are also its most creative, and it proved that our new instruments could listen not only to light, but to the shape of space itself. Multi-messenger astronomy, as scientists call it, became a new way of knowing, a union of senses for a species learning to read the universe's full language. To do this kind of listening requires exquisite patience. The pulses of a single neutron star can be measured for years, each signal recorded and compared. Scientists watch for changes in timing, subtle differences in brightness, shifts in spectrum. From these details, they can infer the star's temperature, its spin rate, and even how thick its crust might be. It's like listening to a song played on a hidden instrument and reconstructing the shape of that instrument just from the echoes. And sometimes, amid the regular data, something unexpected appears. a new frequency, a sudden flare, a faint distortion that hints at something more, perhaps a planet orbiting the neutron star, or the ripples of gravitational waves passing by. In this way, even the tiniest anomaly can open a new doorway to understanding. Every observation is a conversation, every photon a word in a language we're still learning to translate. The most remarkable thing about these tools is not their technology, but their patience. They sit quietly, watching, listening, waiting for faint signals that might take centuries to arrive. The photons that hit a detector tonight may have left their star when dinosaurs still walk the Earth. Yet they arrive faithfully, carrying their stories intact across time and emptiness. The universe, it seems, keeps its records carefully. When astronomers translate those signals into colour, the pictures are haunting. A neutron star's surroundings glow in soft blues and purples, filaments of gas and magnetism curling outward like brushstrokes. Some of the most famous images, like the Crab Nebula, show these filaments twisting in slow motion, feeding off the hidden pulsar at their centre. The heart of that nebula beats 30 times each second, though from this far away, it appears utterly still. Even in that stillness, we can sense the energy flowing outward, the steady exhalation of a star that refuses to disappear. Its light stretched into X-rays shows where particles accelerate near the magnetic poles. Its radio pulses trace the clockwork of its rotation. Its faint gamma rays whisper of the deep processes still unfolding within. And from all of this, one picture emerges. The neutron star is not dead. It's transformed. When you look at one of these composite images, a calm blue swirl glowing in the dark, remember that what you're seeing is the sum of countless senses, human instruments extending our perception into realms no eye could reach. We are, in a way, building empathy for the universe, learning to feel its smallest vibrations, its faintest colours, its whispers of magnetism and gravity. The neutron star doesn't know we're watching. It doesn't need to. It simply continues, radiating, turning, slowing, whispering to the cosmos in all the languages it knows. Our task as observers is to listen softly and to recognize that even in death, a star still speaks in light. There are moments when the universe does not shine. It trembles. The light may fade, the radiation may stop, but space itself continues to move, carrying the echo of everything that has ever collided, merged, or fallen. These echoes are not waves in air or water, they are waves in reality itself. When a neutron star moves, when it spins unevenly or collides with another, it sends a shiver through space-time, a pulse of pure gravity travelling at the speed of light. And though we cannot see these ripples, we can now hear them. Listening to gravity requires an instrument unlike any telescope. Light can be captured by lenses, but space-time needs to be measured with distance and patience. The observatories called LIGO and Virgo do this through the simplest of ideas: light travelling in straight lines. Each detector is shaped like a giant letter L, with two tunnels several kilometres long, one stretching east-west, the other north-south. Laser beams travel up and down these tunnels, bouncing off mirrors so perfectly aligned that they can sense a change in length smaller than the width of a proton. When a gravitational wave passes through Earth, it stretches space in one direction and squeezes it in another. The lasers notice. The interference pattern of their light shifts ever so slightly, a whisper of the universe's motion, written in brightness. It's almost poetic that we measure the shaking of the cosmos with light itself, using the calmest thing we know to record the most powerful events imaginable. For a long time, these instruments heard only silence. Then, one day, in August 2017, the quiet broke. Two neutron stars in a distant galaxy had spent millions of years circling each other, drawing closer with every orbit. With each revolution, they lost a little energy, radiating gravitational waves like ripples on a pond. The orbit tightened, faster and faster, until the two stars finally collided. The waves from that collision raced across space for more than 100 million years before reaching Earth. When they did, LIGO and Virgo recorded them as a brief oscillation, a rising tone that climbed like the sound of something falling and accelerating at once. Astronomers named the event GWW1 Centiphus 7. Within seconds of its detection, telescopes around the world turned to the same patch of sky. They saw a flash, a brilliant burst of light that faded in hours, then days. A kilonova, the long-predicted glow of merging neutron stars, had finally been witnessed. From its light, scientists detected signatures of newly forged elements: gold, platinum, uranium. The heavy materials that fill our jewellery, our technology, even our planet's crust, were being created in that moment by stars dying together. For the first time in human history, light and gravity had told the same story. To describe that event in scientific terms is impressive enough, but to imagine it is something else entirely. Two city-sized stars, each with the mass of the sun, whirl around each other at a quarter of the speed of light. Their magnetic fields clash, their outer layers distort, and tidal forces tear at their surfaces. The air between them glows with radiation. Then, in an instant, they touch. The energy released would outshine the entire galaxy for a heartbeat, and the space around them would stretch and quiver like a drum skin. If you could somehow hear that gravitational wave as a sound, it would begin as a low hum and rise in pitch, a cosmic chirp, brief but bright. Astronomers even play these recordings in lectures, translating gravity into audio. They sound oddly cheerful, like a single pluck of a string, and yet they carry the memory of stars destroyed. From events like these, we've learned that neutron stars are not just remnants, they're storytellers. Each merger reveals more about their inner lives. The way the gravitational wave rises and fades tells us how soft or stiff the stars were, how easily their matter deformed under pressure. By comparing those patterns with theory, scientists can deduce how matter behaves at densities greater than the atomic nucleus, a mystery otherwise unreachable. It's as though nature, in its final act of collapse, offers us a blueprint of itself. Since 2017, more gravitational waves have been heard, mostly from black holes merging silently in the dark. But a few, weaker signals may come from neutron stars colliding, spinning, or even from slight asymmetries in solitary ones. A bump on the surface, a mountain only a few millimeters high, could send out a faint continuous wave, humming through space forever. If our instruments become sensitive enough, one day we might hear that steady song, a single neutron star singing to the universe. The beauty of gravitational astronomy lies in its universality. Light can be blocked by dust or absorbed by gas, but gravity passes through everything. A wave produced on one side of the cosmos will arrive here undistorted, carrying pure information. In that sense, gravitational waves are the truest messengers. They do not blink or fade, they simply arrive, having crossed the void untouched. There's a humility to that idea. These waves existed long before eyes or instruments. They've been rippling through space since the first stars formed, unnoticed, unheard, waiting for a species to build a tool delicate enough to sense them. And now that we can, the universe feels a little more intimate, as if we've finally learned to listen to the background heartbeat of creation. When we combine gravitational and electromagnetic observations, light and space-time together, we enter a new era of knowing. Multi-messenger astronomy is not just a phrase, it's a change in consciousness. It means that no single form of perception is enough. Just as our senses work together to experience the world, so must our instruments. Light shows us beauty, gravity shows us motion. Together, they tell the truth. Each detection, each data point, is a reminder that the cosmos is not static. It quivers, pulses, and breathes. The same physics that governs a falling apple governs the merging of stars. The same gravity that keeps your feet on the ground is capable of bending time and space when concentrated enough. The difference is only scale, and scale, like time, is an illusion we use to make the infinite comprehensible. As gravitational waves fade into the quiet again, the observatories continue listening, patient and still. They know more are coming. Somewhere, out there, another pair of neutron stars is beginning its slow spiral inward, their dance measured in centuries. One day, their final step will reach us as another faint tremor, another soft vibration of space itself. And when it does, our planet will move imperceptibly, stretching and relaxing by less than the width of an atom, as the universe breathes through us. That's what it means to listen with gravity, to let the cosmos speak not in light, but in movement, to recognize that even in silence, the universe has a voice. Long before a collision ever happens, the story of a kilonovae begins as a dance, a slow, spiraling waltz between two neutron stars bound by gravity and time. Out in the quiet dark, these remnants orbit one another in silence, each one tugging gently at the other's motion. They are partners born from ancient supernovae, wandering alone until gravity caught them together. And once the dance begins, it will not end until both are gone. At first, the motion seems almost peaceful. The stars circle each other every few hours or days, each no bigger than a city, yet each weighing as much as the sun. Gravity, so strong that even light bends around them, ties their paths into perfect ovals. But this perfection is temporary. With every orbit, the system leaks energy, tiny amounts of it, carried away as gravitational waves, ripples moving through the very fabric of space. These waves are like the soft music of the universe, invisible yet real, slowly draining the dancers of momentum. As energy leaves, the orbit tightens, the stars draw closer, their pace quickens. It's a waltz that tightens with every step. What once took hours now takes minutes, then seconds. The two bodies begin to stretch one another, tides pulling their crusts into bulges, bending their magnetic fields together. The space between them fills with charged particles and radiation, a bridge of light and force connecting their surfaces. If you could see this moment, it wouldn't look like violence. It would look like grace, the two stars circling faster and faster, tracing luminous arcs in darkness. Yet beneath that beauty lies unimaginable power. Each neutron star is dense beyond comprehension, a sphere where a teaspoon of matter outweighs mountains. Now imagine two such worlds rushing toward each other, their combined gravity curving space itself into a whirlpool. The closer they come, the louder their gravitational song becomes. Though we cannot hear it directly, we can translate it. A chirp, rising in pitch as the stars approach. For millions of years, the sound was too faint for any instrument to detect. But in their final moments, the frequency climbs into a range our detectors can sense, a quick crescendo ending in silence. To the universe, this is music, the final notes of two objects completing a cosmic duet. Just before impact, their orbital speed approaches a fraction of the speed of light. The airless space between them glows with energy. Magnetic fields twist into tight braids, storing tension like stretched cords ready to snap. The stars deform, becoming egg-shaped under the stress, and then, in a heartbeat shorter than thought, they touch. The collision releases more energy than the sun will emit in all its lifetime. The shock tears through their matter, ejecting a cloud of debris that races outward at a fifth of the speed of light. The impact sends a final gravitational wave ringing through the cosmos, and the combined object, whether a new, heavier neutron star or a newborn black hole, emerges from the chaos. Around it, the debris glows in every colour of invisible light, from X-rays to gamma rays. For a few seconds, the event produces one of the brightest flashes known, a short gamma-ray burst. If you could see it in real time, it would appear and vanish faster than you could blink. A flash you could fit between two blinks of your eyes, yet powerful enough to be seen across billions of light years. It's as if the universe itself flickered, a brief reminder of how alive even its dead stars can be. After the initial flare fades, the wreckage continues to shine. The ejected material, enriched with neutrons, expands rapidly into space, colliding and combining in complex nuclear reactions. For hours and days it glows with a strange fading light, blue at first, then red, then infrared, as it cools. This glow is what astronomers call a kilonova, the afterglow of the merger, the visible signature of a cosmic forge in motion. In that expanding debris, something extraordinary happens. Free neutrons racing through the dense cloud are captured by atomic nuclei. In the chaos of heat and pressure, they stitch together to form new elements, those heavier than iron, those rare and precious materials that make up the jewellery of planets and the circuitry of mines. Gold, platinum, uranium, all born in the split second between destruction and creation. It's humbling to think that every ring on every hand, every flake of gold buried in the earth, began this way. Somewhere, long before our planet existed, two dead stars embraced and tore each other apart. Their ashes drifted through the galaxy, mixed with clouds of gas, and settled into the young solar system. When you touch gold, you're touching the cooled remains of that ancient light. For astronomers, watching such an event is both thrilling and solemn. In 2017, when the detectors on Earth recorded the gravitational waves from a neutron star collision, telescopes turned immediately to the sky. They found the afterglow just as theory predicted, first bright invisible light, then fading into infrared as the heavy elements formed. For the first time, humanity saw the creation of matter itself. It was a confirmation, not just of models or equations, but of imagination. Even from hundreds of millions of light years away, the spectacle was visible to our instruments. The flash was faint by human standards, but bright enough for space telescopes to catch. Over the next few weeks, its glow faded, leaving behind only a whisper of radiation and a faint gravitational echo. The dance was done, but its music continued in every heavy atom drifting outward. There's a quiet truth hidden in that violence. Creation often disguises itself as destruction. The universe, in its grandest moments, doesn't simply end things, it transforms them. Two stars die, but in their dying breath, they make the ingredients for new worlds. Every heartbeat of that collision becomes part of something else. Stars, planets, oceans, even us. If you imagine that dance in your mind, try not to picture the explosion. Picture instead the orbit, the slow spiral inward, the glowing connection between 2 points of light, the way gravity choreographs their final embrace. It's less a crash than a merging, a folding together of histories. And when the light finally fades, what remains is a universe slightly richer than before, holding new metals, new dust, and new potential. In the darkness that follows, the debris continues to drift, stretching across light years. Long after the glow disappears, it will still move outward, spreading its gifts through space. Somewhere, billions of years from now, those atoms may gather again under gravity's pull to form new stars, and the cycle will begin once more. So the dance never truly ends. Each merger leads to a new beginning, each death to a new kind of light. What began as two quiet neutron stars circling in darkness becomes the forge of everything bright, precious, and alive. And as the universe keeps turning, it remembers that brief moment when gravity and creation shared the same step, and time itself paused to watch. When the two neutron stars finally collide, the first flash, the gamma-ray burst, is over in a blink. But the real story begins after the brightness fades. The debris, thrown out into space at a fifth the speed of light, starts to cool and condense, and what was chaos becomes creation. The explosion is no longer a simple act of destruction. It has turned into a cosmic forge, one that works in silence and time rather than flame and noise. The glowing remnants spread outward like a tide of molten light, a sphere of gas expanding with unimaginable speed. Within hours, it begins to shine in every wavelength. Blue, then gold, then crimson, the colours shifting as the heat falls from tens of billions of degrees to something gentler, though still far beyond any fire we know. This is the kilonova, the quiet bloom after the storm, the brief moment when the universe takes its raw violence and turns it into beauty. Inside that luminous cloud, atomic alchemy unfolds. In the superheated mix of neutrons and fragments, the laws of physics reach their creative limit. Neutrons move freely, captured by atomic nuclei faster than they can decay. In this race, new elements are born through what scientists call the rapid neutron capture process, the R process. But instead of describing it as a set of reactions, imagine it as a weaving. The universe, with 1,000 invisible hands, threads neutrons into heavier and heavier fabrics, stitching them together into gold, platinum, and all the elements that make the universe sparkle. It's humbling to realise that the jewellery we wear, the coins we mint, even the microscopic traces of heavy metals in our bodies were made this way. Every ring on your finger was once part of a dying light. Every fragment of gold was a note in a cosmic explosion, a silent aria sung by two collapsing stars. In 2017, when astronomers witnessed such a merger for the first time, they watched as this light unfolded exactly as predicted. The first hours were bright blue, the telltale signature of lighter elements being formed. Then, as heavier ones like gold and platinum appeared, the colour shifted to red and infrared. For weeks, telescopes tracked the glow as it faded, and in that fading, they read the story of elemental creation. It was not just confirmation of theory, it was the universe revealing its recipe. The physics behind it is extraordinary, but the feeling it inspires is simple awe. The energies at play dwarf everything humanity has ever created or imagined. In the space of a few seconds, the collision releases more power than all the stars in a galaxy combined, and yet what remains is not devastation, but material, dust and atoms destined to form the next generation of stars, planets, and perhaps life. Even destruction leaves behind beauty. Picture the scene. The kilonova glows like an ember in a black sea, its light fading slowly into the void. Around it, a cloud of new elements swirls. Iron for the cores of future worlds, gold for the veins of mountains, silver for the clouds of distant moons. Some of that matter will drift forever through the galaxy, never settling. Some will fall into new star systems, pulled together by gravity's quiet insistence. Billions of years from now, that same matter may become part of a planet orbiting a sun, where someone might someday hold it and marvel at its shine. It's easy to think of this process as remote, happening far away and long ago. But it's not truly distant. Every atom of gold, platinum, or uranium on Earth is a relic of such an event. Somewhere in our galactic past, before the sun existed, a pair of neutron stars collided, spreading their luminous dust into the cloud that would eventually become our solar system. The Earth was built in part from the ashes of their merger, every sunrise glinting on metal, every instrument made of gold or silver. Every trace of these elements in our blood is a quiet echo of that ancient fire. And it's not only beauty that emerges from such violence, it's stability. The heavy elements created in kilonovae are some of the most enduring in existence. They don't burn away easily and they don't fade. They persist long after the light that made them has gone out. In a sense, they are memory itself, matter remembering the stars that forged it. When we observe a kilonova today, we see the same process that has been shaping galaxies since time began. We're watching the universe refresh itself, creating the raw ingredients for complexity again and again. It's an endless recycling of matter, an eternal act of generosity. The stars die, but they do not hoard their riches. They scatter them freely, so that other worlds may one day shine. There's something almost tender in that idea. The same forces that can crush matter into a ball no larger than a city can also craft gold that glitters in a wedding band. The same violence that can tear apart stars can build the soil beneath our feet. The contrast feels impossible, yet the universe holds both truths at once. It destroys, and through that destruction it creates. When astronomers speak of kilonovae, they use the language of data, spectra, luminosity, decay curves. But beneath those terms is poetry. The glow of a kilonova is the briefest light of generosity, a cosmic exhale where the universe shares what it has made. It's the visual proof that nothing truly ends, that even in collapse there is creativity. If you could watch that fading light without fear or urgency, you might see something strangely familiar. The way the brightness softens resembles the last colours of a sunset, the quiet retreat of day into night. It's as if the universe itself were closing its eyes after a long, magnificent labour. The light diminishes, but the warmth remains in everything it has touched. By the time the kilonova fades completely, only the faintest afterglow remains, a shimmer in the background of the cosmos. The newborn elements continue their journey, unseen but vital. Somewhere far away, another star will form from that dust, and another, and another. In this way, the story of the universe loops back on itself, turning endings into beginnings. The next time you see a ring of gold or a trace of platinum in a circuit, or even a grain of uranium hidden deep in rock, you are holding a fragment of that story. You are touching something that was once a burst of light brighter than a galaxy, a relic of creation that survived billions of years to rest in your hand. And as the universe expands and cools, those moments of creation continue. Somewhere, even now, two dead stars may be circling each other, slowly drawing closer, preparing to collide. When they do, another flash will bloom, brief, brilliant, and unseen by most. But its legacy will endure, scattered among the stars, waiting to become something new. The cosmos, in its quiet rhythm, keeps turning its chaos into art. Somewhere in the silence that follows the kilonova's fading glow, the universe continues its quiet work. The debris cools, drifts, and becomes part of something else. Dust, planets, new suns. But the neutron stars themselves, and their violent cousins, leave behind more than scattered elements. They leave lessons. They are the universe's laboratories, running experiments on a scale no human could ever replicate. They take the laws of physics, the same ones that make a pendulum swing or a candle burn, and stretch them to their breaking points. And in those extremes, they reveal what those laws are truly made of. On Earth, we test matter in machines that can reach enormous pressures and temperatures, but even our most powerful particle accelerators can't compare to what happens inside a neutron star. There, gravity crushes matter to densities trillions of times greater than any solid known. The pressure in the core is so high that it forces protons and electrons to merge into neutrons, creating something beyond ordinary matter, nuclear fluid, perhaps even a soup of quarks. Every theory about what happens inside these stars is, in a sense, a proposal written in the margins of reality. Neutron stars are where the familiar rules of physics meet the unfamiliar ones. They sit at the crossroads between quantum mechanics, the realm of the very small, and general relativity, the realm of the very large. Normally, those two sets of rules ignore each other. but in the heart of a neutron star they must coexist. The particles inside obey quantum laws, refusing to occupy the same space, while gravity outside warps space-time itself into a deep well. It's like trying to mix two languages that were never meant to be spoken in the same sentence, and somehow making poetry out of them. By studying neutron stars, scientists hope to bridge that gap. Every time we observe a pulsar's spin slowing, a magnetar's flare, or the merger of two neutron stars sending gravitational waves through space, we collect clues. The timing of those pulses, the strength of those flares, the pattern of those ripples, they all describe how matter behaves when it's pushed to its absolute limits. What we learn there helps us refine our understanding of the universe everywhere else. For example, the behavior of a neutron star's crust, how it cracks, how it shifts, how it conducts heat, teaches us about the physics of solids under unimaginable stress. The superfluid inside, which flows without friction, helps us understand the strange world of quantum fluids. Even the way the star cools over time tells us how heat moves through dense nuclear matter. These aren't just curiosities, they're windows into the fundamental nature of existence. Somewhere within that dense interior may lie matter we've never encountered. If the pressure is high enough, neutrons could dissolve into their constituent parts, quarks, creating something called quark matter. It would be a new state of being, a kind of continuous fluid of elementary particles. Other theories propose the existence of strange matter, made of quarks that don't exist in normal atoms at all. If such matter is real, it might even be stable, meaning a piece of it, if formed, could last forever. It sounds fantastical, but neutron stars make such speculation necessary. They're the only places where the universe can naturally test these ideas. They are the laboratory benches of the cosmos, conducting experiments with gravity, pressure, and time, instead of glassware and heat. And though we can't step inside them, we can read the results from afar, in the patterns of light and gravity they emit. Neutron stars also remind us that even the most extreme environments still follow patterns, still find balance. For all their density and violence, they remain steady. They spin, cool, and radiate according to rules that can be measured and predicted. This balance between collapse and stability, between gravity and resistance, between quantum order and relativistic curvature, is one of nature's finest tightrope acts. When you think about it, these stars are also metaphors for resilience. They are what happens when collapse refuses to complete itself. They take the full weight of gravity and still stand. Their atoms, crushed to the edge of annihilation, reorganize into something new, a structure that can endure for billions of years. In their persistence, they reflect a truth that seems to echo through all of existence. Even at the edge of failure, nature finds a way to hold form, and just as the neutron star sits at the border between known and unknown, so does our curiosity. We keep pushing, sending our instruments and minds further. We measure pulsars with atomic precision, searching for tiny variations in timing that might reveal gravitational waves or unseen planets. We listen for the faint hum of rotating neutron stars across the radio spectrum, testing how consistent their rhythm can be. Every signal we capture is a data point, yes, but also a conversation. The stars are not speaking to us, but we are learning to interpret their silence. They remind us too of how small we are, and how much larger our understanding can become. The distances involved are almost unimaginable. Hundreds of millions of light years, vast enough that the light from some mergers began its journey before Earth even formed. And yet, through the language of physics, we can connect to those events, comprehend them, and even predict them. The same equations that describe a falling apple can describe the collapse of a star. The same constants that shape the orbit of a planet also govern the twisting of space-time around a neutron star. That harmony between simplicity and enormity might be the most beautiful truth we've ever discovered. There are still questions left unanswered. How exactly does matter behave at densities beyond the atomic nucleus? What happens when a neutron star spins too fast? Does it tear itself apart or transform into something stranger? Could dark matter, that mysterious substance shaping galaxies, also collect inside neutron stars, subtly altering their structure? These questions hover at the edge of our knowledge, waiting for the next observation, the next burst of data, the next mind to connect the dots. But even without the answers, there is wonder. The existence of neutron stars alone is proof that the universe is both violent and delicate, chaotic and ordered. They remind us that extremes are not always destructive. They're also instructive. The cosmos pushes itself to the brink, and in doing so teaches us where its limits are. And so the neutron star becomes not only an object of study but a mirror. It reflects our own curiosity, our own determination to find meaning even in collapse. It tells us that the universe is not cruel in its complexity. It is generous. It invites us to explore, to question, to reach. And though we may never touch the surface of a neutron star, we can still understand its song. They remind us that even certainty has edges, and that's where discovery begins. In the quiet that follows all this cosmic fire, the explosions, the merging, the trembling of space itself, there is a sense of completion. The neutron star has played its part. It has balanced on the edge of collapse, spun its rhythm through the dark and gifted the universe its heavy elements, before finally settling into stillness. But as we step back and look at what remains, something becomes clear. This is not an ending. It is simply another form of persistence. When you imagine a neutron star, it's tempting to think of it as a tombstone for a dead sun. In a way it is. The leftover heart of a once brilliant star compressed into silence. Yet it also keeps giving. The matter it releases, the gravity it exerts, the waves it sends through the fabric of space, all of these continue to shape the cosmos long after the original star's light has vanished. The story doesn't stop with death. It ripples outward, touching everything else. Our world is living proof of that continuity. The calcium in your bones, the iron in your blood, the gold on your hand, each of those elements was born in the heart of a dying star. You are, quite literally, a collection of stellar remains, a piece of the universe that learned to wonder about itself. When you look up at the night sky, you are seeing your ancestors, not in a poetic sense, but in a physical one. The atoms that form your eyes once belonged to something that shone. That realization carries a strange comfort. It means that nothing, not even destruction on a cosmic scale, is truly wasted. The collapse of one star seeds the birth of another. Gravity, heat, and time recycle everything. Even light, when it fades, doesn't vanish. It simply travels onward, stretched and softened by the expansion of the universe, its energy spreading thin but never disappearing. If we could speed up the universe's timeline, compressing billions of years into minutes, we would see this recycling everywhere. Stars ignite, burn and die. Their remains drift into clouds. The clouds collapse again into new suns. The same materials are used again and again, reassembled into infinite variations. The universe is, in a sense, a great act of remembering, a continual reworking of itself. And so, when we look at neutron stars, we aren't just studying death, we're studying memory. We're seeing how the cosmos keeps its experiences alive, encoded in the density of matter, in the faint hum of radiation, in the heavy atoms that endure across epochs. A neutron star is the physical embodiment of resilience, gravity pushing down, quantum forces pushing back, balance found at the last possible moment. If you listen to the quiet around you right now, the hum of a fan, the slow rhythm of your breathing, that same physics is at work. The forces that keep a neutron star stable are the same ones that hold the atoms in your body together. The strong nuclear force, the electromagnetic bond, the steady pull of gravity, They connect everything, from the cells in your fingertips to the orbits of galaxies. You are, in every sense, part of that same pattern. Artists and writers have long imagined stars as symbols of eternity, of souls, of unreachable light. And though the science has replaced myth with measurement, the wonder remains the same. A neutron star sitting alone in its patch of sky, radiating softly in X-rays, is not just a piece of physics, it's a story about endurance. It's what happens when light refuses to quit. Somewhere out there, in a quiet corner of the Milky Way, a neutron star might be spinning still, its pulse faint but faithful, marking time like a cosmic heartbeat. Each rotation, each whisper of radiation, is another second added to the universe's long clock. We will never hear them all, never record every pulse, but the knowledge that they continue, that the rhythm endures, is enough. There's something deeply human about that idea. We too are driven by endurance. We build, we fall, we rebuild. We tell stories of endings only to realize they were beginnings all along. The neutron star mirrors that instinct. It collapses, then stabilizes, burns out, then radiates. It teaches us that transformation is not failure. It's simply the universe's way of continuing. And when we see beauty in this process, when we marvel at the symmetry of gravity and light, it's not just appreciation from a distance, it's recognition. We are made of the same ingredients, governed by the same laws, subject to the same cycles of creation and decay. The difference is scale, not essence. You're to the universe what a neutron star is to the galaxy. A point of consciousness balancing between chaos and order, small yet connected to everything. Eventually even neutron stars will fade. They will cool, slow, and slip into invisibility, their heat and magnetism long spent. Perhaps, in Does far future, they'll merge again, reigniting a spark of creation before finally dissolving into black holes. But even then, their story won't end. The matter they leave behind will continue to circulate, woven into the endless fabric of existence. Maybe that's the truest legacy of these stars. They remind us that permanence is not about remaining unchanged, but about continuing to participate. Everything you see, everything you are, is the product of participation. Every atom has danced through other forms, other lives, other fires, and so will we. When we speak of the universe as ancient, it isn't age we're describing, it's continuity. Billions of years are just the slow turning of a single immense heartbeat. The neutron star, quiet and steady as one of those beats, a pause in the great rhythm that began long before we were here to hear it. And as we drift toward the end of this journey, maybe the most comforting thought is this. The universe is not a place of endings, but of returns. Light fades only to become warmth somewhere else. Stars die only to feed the birth of others. Even silence, if you listen closely, carries echoes of all that came before. So wherever you are listening from, whether you're awake, half dreaming, or already sliding into sleep, know that you too are part of this endless cycle. You're made of stories that began in fire and will continue long after. The stars have their endings, and so do we. But like them, our endings are not really ends. They are beginnings folded back into the fabric of everything. And somewhere in that vastness, a neutron star turns once more, faint and steady, keeping time for us all.